Hi everyone, in this video I'm going to go over section 4.1, which is about L'Hopital's rule. This section I think will be kind of nice for some of us because I think especially for this class since the beginning of the quarter we've really gotten a lot better at algebra as a whole anyway, and a lot better at just mechanical aspects of taking derivatives, which is really what this section is going to require. So as we discussed in 4.1 and 4.3, we still need a way to figure out when we have absolute maximum and minimums on an open interval. So that's an open interval where we can't just plug in the endpoints to see if they're bigger or smaller. Eventually, L'Hopital's rule is going to help us do this, but first we need to learn what the rule is, how to utilize it, and then see how it sort of gets us back to the beginning of the part of the course. So it's really nice having this section at the end because it allows us to review some things that we've talked about before. All right, so the first thing we need to recall is at the beginning of the quarter, we took limits, and then there were some times when we had the limits after we ran it in a form where we couldn't really tell what was going on. So remember, we'd run it through and we'd say, 0 is in the denominator, I have 0 over 0, or infinity over infinity, which we knew didn't really tell us much. So let's recall from the beginning of the quarter, we talked about what we call an indeterminate form. For example, okay, if I have something like 0 over 0 after I run the limit, I don't really know what's going on. If I have infinity over infinity, okay, infinity is not a number, so I can't just divide those. I don't know what's going on. If I had negative infinity over infinity, don't know what's going on. 0 over, actually that doesn't matter. I could keep going with this. I could say infinity over negative infinity, etc., etc. But basically, just remember, you have an indeterminate form, you don't know what's going on. Before, we might have done some more algebra or used a graph or plugged numbers in to see what's going on. Now we're going to learn a different strategy, and that's what we call L'Hopital's rule. All right, so L'Hopital's rule says that if we have functions f and g that are both differentiable and g prime of x, so the derivative of g, is not 0 on some open interval, that means parentheses on the ends of the interval, that contains a except for maybe a itself, okay, and we also suppose the following, and that is that the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is 0, or the limit as x goes to a of f of x is positive or negative infinity, and the limit as x goes to a of g of x is positive or negative infinity. So if those things are true, okay, then what this actually does is puts us into, or gives us indeterminate form. So if we have these things being true, it is true that the limit as x goes to a of f of x over g of x is equal to. All right, so this fraction, what we get, if we look at the top of here, we know if the limit as x goes to a of f of x is 0 and of g of x is 0, we'd get indeterminate form in this expression right here. So we'd get 0 over 0. So that's setting us up for that. Similarly, in the bottom part, if we have infinities for this, it's again setting us up for indeterminate form. So really what this is saying is, if we have indeterminate form, then when we use L'Hopital's rule, so we mark this with a little h, I'll write that in a minute, this is equivalent to the limit as x goes to a of f prime of x over g prime of x. Okay, so I'm going to write this in here. This symbolizes, okay, you're using L'Hopital's rule. All right, and in layman's term, what this means is if you run a limit in its indeterminate form, you can take the derivative of the top and the bottom separately in order to get your limit, as long as the derivative of g, the bottom, is not 0, which would of course make it undefined and not help us very much. All right, so that is what that means in layman's term. I don't think that it's really obvious as to why this is true. So now let's think, okay, well, why does this work? Why does it make sense? All right, if you think about it, if we look at the function f of x separately and g of x separately, which we know by the limit laws, we can look at the numerator and the denominator separately. When we zoom in, which notice that we're taking the limit up here, right? The limit as x goes to a. So when we zoom in on that little point a, our function is going to look very linear. So as we get closer, okay, it will appear to be linear, our function will. So since it looks linear, we know that the limit will look just like the derivative. So I'll write this. Okay, so if we think about our function, okay, f, just the function for now, f of x over g of x. All right, if we zoom in really, really close to one spot on those functions, it's going to look linear. So it will look something like m1, so that's just the slope, times x minus a, right? This is just an equation of a linear function, over m2, so that's the slope of your second function, times x minus a. All right, here, the x minus a's divide out, so you just have m1 over m2. So notice you're left with the slope as the result. Well, we know that the derivative is really representative of slopes. Therefore, what we can turn this into is what we have above, and that is the limit as x goes to a of f prime of x over g prime of x. Right, so we're really just focusing on those slopes because when we zoom in, everything is going to look mostly linear, so we can use those to approximate the limit. All right, so that's most of it for just the reasoning part of this. Hopefully that makes some sense. All right, so now that I've gone through the reasoning, I want to run through several examples. And I'm going to scroll down. Whoa, sorry. Okay, so first example, let's say we have the limit as x goes to 3 of x minus 3 over x squared minus 9. Right, the first thing I suggest doing is just trying to run the limit. So try to run the limit. There's no need to go to extra measures if you can just run it. But notice if you run the 3-2, we do get indeterminate form. So this is definitely an indeterminate form. Indeterminate form. Right, the next thing I suggest trying, you don't have to, is algebra, and that's just because sometimes it makes it easier. So notice that, okay, if we take this, the limit as x goes to 3 of x minus 3 over x squared minus 9 can actually be simplified. So x squared minus 9 factors to x minus 3 times x plus 3. Therefore, the x minus 3's divide out to 1. And we're left with the limit as x goes to 3 of 1 over x plus 3. Notice here we can run the limit and get the result. So this is simply 1/6. All right, so if we can, it's kind of nice to use algebra. Right, sometimes people ask, well, do I have to? Can I just use L'Hopital's rule if I want to? Let's see. So let's say that you chose not to use algebra. And you want to know if you could just use L'Hopital's rule instead. So if we do, we have the limit as x goes to 3 of x minus 3 over x squared minus 9. All right, I'm using L'Hopital's rule, so I put a little h. Important things to know. I can only use L'Hopital's rule if I have a fraction. That's the way that it's defined. I have a fraction, so that's good. It also needs to be or should be an indeterminate form. This is an indeterminate form if I run the limit right now. So using L'Hopital's rule is valid. Right, taking the derivative of the top, I get 1. So the limit as x goes to 3 of 1 on top. Taking the derivative of the bottom, I'd get 2x. Right, so now if I try to run the limit, I can run it through. So here I just put an equal sign. I'm not using L'Hopital's rule again. At this point, I'm just running the limit. So I'd have 1 over 2 times 3, which is 6. So notice you get the exact same thing if you do this algebraically or use L'Hopital's. L'Hopital's rule will be an option. The algebra may not always be an option, as we saw at the very beginning of the course. All right, let's take a look at example 2. So for example 2, first let's run the limit through quickly. So let's check it. All right, if we run this through, we do get a 0 over 0, so it is an indeterminate form. Indeterminate form. All right, second, we can try to use algebra on this. So let's see, if we use algebra, I think it's going to get us somewhere. So we have the limit as x goes to -2. Okay, the top is the sum of cubes. So if you remember this, you could factor the top into x plus 2 times x squared minus 2x plus 4 all over x plus 2. The x plus 2's divide out. So we're left with the limit as x goes to -2 of x squared minus 2x plus 4, and we can actually go through and run that. So if we run that limit through, we would end up with 12, I believe. So this is equal to 12. All right, check that. So run the -2 through. Let's see, you'd get a 4 plus 4 plus 4, which is 12. Right? If you didn't want to use algebra, or let's say you're like, oh shoot, I forgot, how to factor the sum of cubes, L'Hopital's is still an option. Okay, and that's because this is a fraction in its indeterminate form, so we know L'Hopital's rule could also be a good move. Right? If we choose to do L'Hopital's on this, rewrite the question real quick. Right, I need to include my notation, so I'm specifying that I'm using L'Hopital's rule by putting the little h there. Right, if I take the derivative of the top, sorry, I have to write this real quick. The derivative of the top, I'd get a 3x squared. Right, if I take the derivative of the bottom, I get 1. Right, so now I notice I can in fact draw an arrow so you can see that. I can in fact run my limit. So if I run the limit through the top, I get 3 times -2 squared, which is still 12, and that's exactly what I would have gotten or expected to get from my algebra. Okay, all right, let's move on to example 3. All right, so looking at example 3, we have the limit as x goes to 0 of the tangent of 3x over the sine of 2x. All right, so first we can try to think, all right, well, what happens when I run this through? So if you run this through, you would again get 0 over 0. So this is definitely an indeterminate form. So indeterminate form, yes, and it's a fraction, so that's good. Now, if we try to do algebra on this, it's going to get us nowhere. We could try to convert this, but the angles in here are different, so we can't simplify. Can't simplify. All right, and that means that our option is L'Hopital's rule. Must use L'Hopital's. Okay, so if we use L'Hopital's, we'd have the limit as x goes to 0 of, for the derivative of the top, we would get the derivative of the outside is secant squared of 3x, remember the derivative of tangent is secant squared, times the derivative of the inside is 3. All right, over. Okay, on the bottom, the derivative of the sine of 2x, we need the chain rule for, so the derivative of the outside is cosine of 2x times the derivative of the inside is 2. Okay, so from here, let's see if we can in fact run our limit through. So if we have, let's see, if we push the limit through the first part, that would be 3 times secant is the same as 1 over cosine. So 1 over cosine times 3 times 0 squared, right, divided by 2 times the cosine of 2 times 0. Right, for this, in the denominator, we just get a 3 times 1. All right, cosine of 0 is just 1, so you get 1 over 1, and that's 1, over 2 times 1 for the same reason. Therefore, our answer is 3/2. And we use L'Hopital's rule to do this. Notice with my notation, I wrote L'Hopital's on the first one, because that's where I took the derivative. On the second and third steps, I'm just running the limit and doing algebra, so it doesn't make sense to, I shouldn't say algebra, I should say arithmetic, so it wouldn't make sense to write that I'm using L'Hopital's. Okay, so let's move on to example 4. All right, looking through example 4, if I run my limit immediately, I would get 8 to the 0, which is 1, minus 5 to the 0, which is also 1, so 0 on top and 0 on the bottom. So this is definitely in indeterminate form. All right, thinking about this algebraically, I can't simplify, so that's not going to help. And this tells me that I need to use L'Hopital's rule. All right, so let's go through that process. Start off by using L'Hopital's rule. Rewrite the limit as t goes to 0. And I need to take the derivative of the top. So the derivative of the top is the natural log of 8 times 8 to the t times 8 to the t minus the natural log of 5 times 5 to the t. The derivative of the bottom is 1. All right, so I've done that once. I can see that if I run t goes to 0 through this, I have a 1 in the denominator, so I can definitely push this through. All right, so if I run the 0 through, I'd get ln of 8 times 8 to the 0 minus ln of 5 times 5 to the 0. All right, and of course the 1 just stays down there. I don't really need to write it. Right here, 8 to the 0 is just 1, so I'm left with a natural log of 8 minus 5 to the 0 is also 1, so minus ln of 5, and that would be my final answer. So on this one, again, L'Hopital's was our only really good option. We could probably plug stuff into the calculator and try to see what happens, but this is a much more concise, efficient way, so this is definitely the stronger method.